Okay, so we're going to do 3 calculus-based problems here for the Chapter 7, which is potential energy and conservation of energy. So we'll start off with 728. So what we have is we have this object, proton, and it's going to be moving in this coordinate system, x, y coordinate system, where x goes from -1 to +1, and y goes from -1 to +1. And in this case, the force vector is only in the x direction. It's always in the x direction. There's no y component. Okay. So it's got a negative sign here. So when it's when x is positive, it'll be pointing from right to left, and when x is negative, it'll still be pointing from right to left, because this squared is always positive. So the force is always pointing from right to left. Let's go in that direction. So that's the force vector. Now, part A says that they want you to calculate the work going a straight line from 0.10 meters x, 0 meters y, to 0.10 meters x and 0.40 meters j. So if we plot those points, it'll be here and here. So this is the path it's going to take. It's a straight line path. Now, because the force is pointing from left to right, from right to left, and the path is vertical, the work done in this case is just 0. And that comes to, let me just make sure that I'm not, I think you actually have to go back. Well, yeah, it's, if you look in your book, in terms of the work, there's, you take the dot product, and the dot product says that, you know, if your force is in the direction of movement, then you get the full effect, and if it's perpendicular, you get nothing out of the whole thing. So, you know, work is equal to the integral of F dot dl. And because the force is in the x direction and the movement is in the y direction, the dot product of those two is going to be 0. Now in the second case, I got to find my problem again here. Bear with me. So get to the problem. Okay, so B says we go from 0.10 to 0.30. So what I'm going to do is still use the same graph, but I'm going to move this out of the way, get rid of this point. So we go from here to here. So the directional vector is this way. Now, because this directional vector is going from left to right and the force is going from right to left, when we evaluate this particular dot product, you end up with a -1, because they're going in opposite directions. So the work, in terms of just scalar numbers, is going to be the force. There's going to be a negative sign because of this difference in the directions. And then you're going to have to integrate this thing. So you take the, so we got to make sure we don't double dip here. So because the negative sign here reflects this direction, so I don't want to do it twice. So that negative sign is that negative sign. So I don't need to include it again. So I get alpha x squared, and we integrate with respect to x from x1, which is 0.1 meters, to x2. So we go from here to here. So you can take alpha outside the integral sign. When you integrate x squared, you get x cubed over 3. And then we'll evaluate the integral between x1 and x2. So we got the work going from here to here is negative alpha x cubed. Okay, so now what we're going to do is we're going to evaluate the integral at the two limits. So we have x2 cubed minus x1 cubed. So that's this x cubed evaluated at the two values of x. So we can go ahead and plug alpha in now, which is 12 newtons per meter squared. Divide by 3. That comes from the integration part here. x2 is 0.30 meters, and we cube that, and we subtract x1, which is 0.1 meters cubed, and we cube that. So we get that the work is going to be a negative quantity. So it's negative 12 divided by 3 times 0.3 cubed minus 0.1 cubed. So we get the work is equal to negative 0.104. And the units are Newton meters, which are the same as a joule. So you get that. Again, this makes sense because from an energy perspective, if you have a negative work, then you have an increase in potential energy. So as we go this way, we're moving in the direction opposite the force, and that means an increase in potential energy. So now the next one is we basically go the other direction. So we go from 0.3 to 0.30 to 0.10, and so nothing changes except for the sign. We're still doing the same integral. We're just going from x2 to x1, so that's just going to flip these around. So you'll get positive 0.104 joules going that way. And the final question is the force conservative? And the answer is yes. Because a couple of reasons. One is because the work going one direction is negative the work going the other way. Now, so what are forces like this? Well, gravitational attraction is like this. Electrostatic attraction or repulsion is like this. So those are all conservative things. An example of a non-conservative situation is if you had something you were sliding from left to right on a surface and you had the friction force go this way. Whereas if I switch them and go the other way, then the friction force changes. So in our case, the force direction is always consistently the same direction. Whereas here, between going one way or the other, the friction force changes direction, and so that makes it a non-conservative force. So as long as the force is just based upon the location where you are and not the direction that you're moving, then it's going to be conservative force. Okay, so that's the first problem. The next one, we're going to do 731. And this is where you're using potential energy to calculate force. So in this case, we're given the potential energy is equal to alpha times x to the fourth, where alpha is equal to 0.630 joules per meter to the fourth. And what they do is they ask, what is the force, magnitude, and direction when the particle is at x equals negative 0.8? So to get the force, we use this relationship that the derivative of the potential energy with respect to x is equal to negative the direction of the force in the x direction. In the previous problem, we calculated potential work, which is related to potential energy, directly by integrating the force through a distance to calculate the work. Here, we're given the potential energy, and then we want to calculate the corresponding force. So all we have to do is take the derivative of this expression. So the derivative of u with respect to x is going to be 4 alpha u cubed. And they say, so to find, so that's the derivative, so that's equal to minus the force in the x direction, or the force in the x direction is equal to negative 4 alpha u cubed. Not u cubed, x cubed. This is x. So to evaluate this, you just plug in alpha and x. So they were looking for at x at negative 0.800 meters. So we get negative 4 times alpha, which is 0.630 joules per meter to the fourth, times x, which is negative 0.800 meters quantity cubed. So negative 4 times 0.360 times negative 0.8 quantity cubed. So we get the force in the x direction is equal to positive 1.29 newtons. And since it's positive, it's going to be pointing from left to right. Let's see if that's the right answer. 1.29 positive x direction. Okay, so that's just an example of how you can go from a potential energy function to a force. And the last problem is this one, 7 to 33. So what we've got is this object that's moving around in space. And the way we'll do this, since we're moving in like 10th units, we'll make this a +1 in the y direction. This is -1. This is +1 in the x direction. This is -1. And, you know, we've got some little object, just showed as a little square, like that. So we're going to move this around. And what we're given is that the potential energy function as a function of x and y is equal to 5.80 joules per meter squared x squared I. Well, you don't have to put an I, because potential energy is a scalar quantity, not a vector quantity. So that's why we don't have I's and J's. Force, on the other hand, is a vector quantity. But you can, that's the cool thing about potential energy functions, is those are scalars, and if you want to get more information relative to vectors, you just take the derivatives with respect to different directions. So in this case, the force in the x direction is the derivative of u with respect to x, and the force actually is a negative sign here. Force in the y direction is negative du dy. To be more exact, it's a partial derivative. But let's just, what we do here is, if you have a partial derivative, you, with respect to x, you assume anything with respect to y can be treated as a constant. So when I take the derivative of u of x and y with respect to x, this goes to 0. And you get the first case, which is 2, and we got this, you get negative from here. So you get negative 2 comes from the exponent, times 5.80 joules per meter squared times x. And then when you do the y, you'll have this negative sign will cancel out that negative sign. And then you'll have the exponent 3 when you take the derivative. 3 times 3.60 joules per meter cubed times y squared. Again, this gets treated as a constant when you take the derivative with respect to y. Now, from an acceleration perspective, the acceleration in the x direction is just the force in the x direction divided by the mass. And the acceleration in the y direction is equal to the force in the y direction divided by the mass. So the first thing we're going to do is we're going to evaluate these at the given values of x and y. So in this case, x is 0.3 meters and y is 0.6 meters. So to find the force in the x direction, we have -2 times 5.80 times x, which is 0.3. And the units will work out to be newtons. So we have -2 times 5.8 times 0.3, which is -3.48 newtons. And down here, we'll plug in 0.6 for y. So we'll have 3 times 3.6 times 0.6 squared. 3 times 3.6 times 0.6 squared. And I get plus 3.89 newtons. So the very corresponding accelerations are going to be the forces divided by the mass, which is given in the problem as 0.04, I believe. Yeah, 0.0400 kilograms. And the units will work out as meters per second. So I get -87 meters per second squared. And here I get -97 meters per second squared. Now what they're asking for is the total velocity, so we have to put this together as a vector. So I'm going to just kind of sketch this out just to get kind of a direction for this thing. So we've got a negative x component and a positive y component. So it's going to look something like this. So the angle is going to be between 90 and 180 degrees. So that's the angle theta. Now, the magnitude of the acceleration is just using the Pythagorean theorem. So we take -87 squared plus positive 97 squared. So 87 squared, I used it 87 instead of -87 because when you square it, the sign kind of doesn't matter. And then you take the square root of that and you get 130 meters per second squared. So that's the length of this vector. And the theta, well, what we do is we figure out the reference angle here. So that's my reference angle. And what we do is we take the inverse tangent of the absolute value of the y component, which is 97, divided by the x component, which is -87. So inverse tangent of 97 divided by positive 87 is 48 degrees. And so the angle from the positive x-axis is going to be 180 minus 48, which is 132 degrees with respect to the positive x direction. So that's the answer. So, what did we do here? We said we could figure out the forces, the components of the forces, by taking the derivative of the potential energy function with respect to x and y, assuming that when we take it with respect to x, the y is considered a constant. The same with this one. Once we had the x and y components of force, we could calculate the x and y components of acceleration, and then we combined it into a single vector and calculated its magnitude and direction just using normal trigonometry.